Welcome back. Here is the next exciting video in this series of organic reactions, this time elimination reactions. Essentially, these are the opposite to addition reactions. This definition needs to be remembered and used whenever you're talking about elimination reactions. In these, the functional group, which is either an OH or a halogen, and a hydrogen atom from an adjacent carbon are removed, and a carbon-to-carbon double bond forms in their place. So we're going from a saturated to an unsaturated molecule. At this level in NCEA, we only need to be concerned with two elimination reactions. The first one is where we're removing the halogen and an adjacent hydrogen. And the second one is when we're removing an OH and an adjacent hydrogen as water. Neither of these can happen on their own, so they both need a pretty significant catalyst. For the hydrogen halide, you need KOH or NaOH, but it needs to be an alcohol, not aqueous. If it's an aqueous, the substitution reaction occurs. For the alcohol, we need conc H2SO4. Conc H2SO4 is a dehydrator, which means it removes water. This is exactly the opposite of adding dilute water into alkene. So let's take a look at these two reactions in a very simple reaction scheme. Just at the back of your mind, remember in these elimination reactions you always finish with an alkene, that's your product, and it's essentially the opposite to addition. So here we have propan-2-ol and 2-chloropropane. Both of these can undergo elimination reactions. We need to add concentrated H2SO4 to the alcohol, and this will remove the OH and an adjacent hydrogen. And if we add alcoholic KOH or NaOH to 2-chloropropane, it will remove the Cl and an adjacent hydrogen. Both of them finishing up with the alkene propene, plus H2O for the alcohol, and plus HCl as a byproduct for the haloalkane. Just like in addition reactions, where sometimes we could get two products from one reaction, we can sometimes get two products in an elimination reaction. And Zaitsev's rule tells us when to apply this and what the major and minor is. So let's take, for example, 2-chlorobutane, which can undergo an elimination reaction with KOH or NaOH in alcohol. Remember that the functional group will always get removed, but if we remove this adjacent hydrogen off carbon 1, we will make this product, but-1-ene. And if we remove the hydrogen from the second possible adjacent carbon, this one here, we will make a second product of but-2-ene. So one of our requirements is that there must be two adjacent carbons to the one with the functional group. But there's also another requirement, and that is that those two adjacent carbons must be asymmetrical. The one on the left here has 3 hydrogens, and the adjacent carbon on the right has 2. So we're going to call carbon 3 the poor carbon with fewer hydrogens attached. Seeing as the rule is called the poor get poorer, removing the hydrogen from carbon 3 gives us the major product, in this case but-2-ene, and therefore removing the adjacent hydrogen from carbon 1, the richer carbon, gives us the minor product, in this case but-1-ene. In both cases, HCl will be a byproduct. Just one last thing, if you produce but-2-ene as your major product here, you can also form cis and trans isomers, and this is something to look out for. That's the end of this video. In the next one, we'll look at oxidation and reduction.